Okay, so here's problem 1, chapter 10. And yeah, there are a couple of problems in there that probably do need some explanation, which you never got around to in class. So it says we have a copper wire with a length of 11 meters and a cross-sectional area of 2.4 times 10 to the minus 5 meters squared per second. And is stretched taut between two poles under tension of 75 newtons. What is the tension in the wire when the temperature falls by 10 degrees C? So this actually goes back to using some of the information in our chapter 10. So let us look at this thing. So you've got this copper wire that's stretched between two poles. Okay, so the length is equal to 10 meters. And the area, cross-sectional area, is 2.40 times 10 to the minus 5 meters squared. And the tension, which is a force, is equal to 75 newtons. Okay. So what you can do is you can figure out, this is using the relationship that says stress is equal to the modulus of elasticity times strain. And so what we can do is we can figure out how much strain there is. It's like our initial delta L. So remember, stress is force per unit area, and E is a property of the material. And strain is the change in length divided by the original length before it was stretched. So what we can do here is you can figure out, and really this 10 meters relative to the length, we could almost say L0 is 10 meters just to, I mean, it's really, this is really L0 plus delta L. But we can, so I'm just going to say L is equal to L0 plus delta L. We'll do it exactly right here. So we're going to do that. This is just the temperature, the original temperature, whatever that is. So we have a force, we have an area, we know that L is 10 meters. So what we can do is we can solve for L0. L0 is going to be equal to L minus delta L. So we could put that up here. So delta L over L minus delta L. What we're going to do is solve for delta L. Basically, how much do we need to stretch it to cause the initial conditions? And, well, actually, the difference between L and delta L, L0 is so small, it just makes the problem easier. So I'm gonna use L here instead of L0. It's not going to cause that much of a difference in our calculation. So you can solve for delta L. We just need E for copper. So if I go to the book, and this is the book that you have, and we would look under Young's modulus in the table, in the index, because I don't know exactly what page it's on. So let's see if there's a thing that says Young's modulus. X, Y, Z. Okay, it's not under Young's, so it's probably under elastic modulus. So we'll look under elastic modulus. There we go, 347. Or there, Young's modulus under elastic modulus, so it's 348. So we'd go to page 348. And actually it's on 349. Approximate elastic modulus for copper is 11 times 10 to the 10th pascals. So E is equal to 11 times 10 to the 10th. So now let's solve for delta L. So delta L is force per unit area. So what I'm going to do is I'm just going to divide by this, multiply that by that. So I'm going to multiply by L, divide by E, and that should give me the number I'm looking for. So my force, I had 75 newtons as the tension. I divide by the area, which is 2.4 times 10 to the minus fifth. 2.4 times 10 to the minus fifth meters squared. I multiply by the length, which was 10 meters, I think. 10 meters. And I would divide by 11 times 10 to the 10th. The units are pascals, which are pascals in newtons per meter squared. And if we look at the units, newtons cancel out with newtons. I've got newtons per meter squared here. So this meter squared cancels that out. And I just landed with meters, which is what I'm looking for. Delta L should be meters. And it should be pretty small. 75 times 10 divided by 2.4 e to the minus 5 divided by 11 e to the 10th. And so I get delta L is 2.84 times 10 to the minus 4 meters. So you see it's relative to L0 and L are pretty darn close to each other in our case. So for the accuracy we're looking for. So that's the amount of how much it has to stretch to get the initial tension. Now, it says what is the tension in the wire when it falls by 10C? So what's going to happen is that the wire is going to want to contract. It's want to get shorter, but it's going to be restrained. So it's going to hold the length. So what we do is we calculate the change in length due to temperature change, and we're going to add that to the change in length originally in the tension of the wire. So this is a delta T with respect to temperature, and we know that is going to be alpha times delta T times L, the original length. Or delta T over L is alpha times delta T. So the temperature change doesn't matter. It's saying it's temperature change in Kelvin, and C is the same. So we look for linear coefficient of thermal expansion. Linear. So let me just say, let's look into thermal. Thermal expansion, linear. Okay, this is on in the index. Thermal expansion, linear, 551. So we go to page 551 to both. So, actually, if you go to 552, you'll see coefficients of linear expansion. Copper, 1.7 times 10 to the minus 5. So alpha is equal to 1.7 times 10 to the minus 5, and the units are inverse C. Okay, then you multiply by delta T, which is 10 degrees C. It is actually negative 10 degrees C, so because it's going to get shorter. And we multiply by the length, which is 10 meters. So this is the additional amount that the wire wants to contract. So we take 1.7 times 10 to the minus fifth times negative 10 times 10 meters, and we get delta L due to the temperature is 1.7 times 10 to the minus 3 meters. Yep. Okay, so you can see that on the order it's almost 10 times the change in length just due to the original tension. So we're going to add those together. So our total delta L, let's say delta L total now, that we use in the calculations is 2.84 times 10 to the minus 4 meters plus 1.7 times 10 to the minus 3 meters. And you do that, and you're going to get 2.84 e to the minus 4 plus 1.7 e to the minus 3, and I get the total delta L as 0.0020 meters. Okay, I'm just going to pause for a second. Okay, so I was just checking to make sure I was doing everything correctly, which I am. Okay, so now we go back and we use this relationship here, but we solve for the force, because what they're asking for here is what is the tension at the lower temperature. So if we solve for force, force is going to be equal to delta L divided by L times E divided by, actually E times area. Okay, so force, let's make sure we did this right. Force is delta L divided by L times A. Okay, and we should get the right units when we do this. So we're going to use the total length, and we're going to divide by the 10 meters for the total. For the length, modulus was 11 times 10 to the 10th newtons per meter squared times the area, which isn't changing. The cross-section area is 2.4 times 10 to the minus 5 meters squared. And you see these meters cancel out. These meters cancel out. You just end up with newtons, which is what we're looking for. So 0.002 divided by 10 divided by 11, times 11 e to the 10th times 2.4 e to the minus 5. And I get that the force, the tension is 528 newtons compared to the original 728. And I'm just going to check my answer. Yep, okay. So I probably can only use two significant figures because of the way I did the problem. So I get 530 newtons. So let's explain what we just did. So we had a copper wire that it was initially 10 meters in length stretched with a cross-sectional area such with a tension. So I used this relationship to find out what the delta L would be from, and I assumed that delta L was much smaller than L, so that I could, instead of using L0 here, the initial length, I could use the stretch length. So I found an increase in length associated with the tension of 75 newtons. Then, so I'm stretching that. So now I'm cooling it down so it wants to contract, so I have to pull harder to keep it from getting shorter. And I find the length that it would normally contract without, if it isn't restrained, to be 1.7 times 10 minus 3 meters. So the total amount this thing is stretched based compared to its initial unstretched condition is you have to stretch it 2.84 times 10 to the minus 4. And the original condition, you have to stretch it another 1.7 times 10 to the minus 3 meters to make it so that it's 10 meters after both things have happened. And then you use the relationship between stress and strain and the Young's modulus to back out the higher tension that results from the cooling down